Hello everyone, good day. How are you? I hope you are all doing fine. And I would like to share a quote. It says that success is not final and failure is not fatal, but it is the courage to continue that counts. So let us always continue to learn new things, and today I would like to share my knowledge about thermodynamic processes. I am Ruben Matam, taking a Bachelor of Secondary Education, major in General Science. So there are four thermodynamic processes. We have isothermal, isobaric, isochoric, and of course, adiabatic. So let us look more deeper into these processes. So let us start first with isothermal process. So isothermal is a process in which the temperature of the system is kept fixed throughout. The transfer of heat into or out of the system happens so slowly that thermal equilibrium is maintained, hence change of temperature is equals to zero, or simply the temperature is constant in isothermal process. So we have here two images, expansion and compression of ideal gas. So in the first image is a compression, the second image we have expansion. So in an isothermal expansion, the gas absorbs heat and thus work, while in an isothermal compression, work is done on the gas by the environment and heat is released. However, with that compression or expansion, as we can see, temperature is still the same. So this is the isothermal gas. So since for an ideal gas, the internal energy is proportional to temperature, it follows that there is no change in the internal energy of the gas during an isothermal process. The first law of thermodynamics then becomes change in internal energy is equals to zero and heat transfer minus work, or heat transfer is equal to work. All the heat added to the system is used to do work. So that is in isothermal processes. Let's look at examples of isothermal processes. There are actually several examples, but these are the most common example of isothermal. So changes of state or phase changes of different liquids through the process of melting and evaporation. Take note, this is only when the process of changing phase of a liquid is through melting and evaporation that it can be considered as an isothermal process. Another example of isothermal is we have heat pump. So the heat is either removed from the house and dumped outside, or the heat is brought inside the house from outside to warm the house. In either case, the goal is to keep the house at the desired temperature setting. So that is how heat pump is an example of isothermal. Another example is, I know you are all familiar with the refrigerator. So refrigerator works isothermally. A set of changes takes place in the mechanism of a refrigerator, but the temperature inside remains constant. Here, the heat energy is removed and transmitted to the surrounding environment. So that is how refrigerator is considered an isothermal process. Let us move on to the next thermodynamic processes, which is isobaric. So the term isobaric has been derived from the Greek words iso and baros, meaning equal pressure. When a system expands at a constant pressure, its volume is increasing, and this corresponds to an output of work. Hence our equation, work is equals to negative pressure times change in volume. So always remember, in isobaric, The constant one is pressure. One example of isobaric is hot air balloons. So how come that hot air balloons became an example of isobaric process? So here it is. Hot air balloon works because hot air rises, right? By heating the air inside the balloon with burner, it becomes lighter than the cooler air on the outside. So this causes the balloon to float upwards as if it were in water. So the pressure inside the balloon is the same as the atmospheric one. When the pilot injects heat into the air, the temperature rises. It decreases the density of the air, and because of the difference between its density and that the air, the balloon goes up. Thermodynamically, part of the heat is converted into work, making the hot air balloon rising up. Part of this heat is released outside the system because of thermodynamic contact of external air and because of the loss of hot air when it is expanded. So that is how hot air balloon goes up, and that is a work of an isobaric process. So let us proceed to the next thermodynamic process, which is isochoric. So if isothermal has constant temperature, isobaric has constant pressure, isochoric is a thermodynamic process taking place at constant volume. So constant volume. So the term isochoric has been derived from the Greek words iso, meaning constant or equal, and choric, meaning space or volume. It is also sometimes called as an isometric process or constant volume process or isovolumetric process. So in an isochoric process, whether the pressure change is positive or negative, the work done by the gas in an isochoric process is zero. Take note, the work done by the gas in an isochoric process is equals to zero. The total heat supplied or rejected is also equal to the increase or decrease in the internal energy of the system. Hence, our equation, heat transfer is equals to the internal energy. So one example of isochoric is we have Otto cycle. Otto cycle is actually a good example of an isochoric process. So in this, when the gasoline-air mixture is burned in a car's engine, there is an increase in the temperature and the pressure of the gas inside the engine. Meanwhile, the volume of the gas remains exactly the same. So that is how Otto cycle works. Next, we also have our adiabatic process, our last process in thermodynamic. So the thermodynamic process in which there is no exchange of heat from the system to its surrounding, neither during expansion nor during compression, is adiabatic process. So take note, there is no exchange of heat from the system either during expansion nor during compression of ideal gas. So there are essential conditions that must be met in order for adiabatic process to take place. So first thing is the system must be perfectly insulated from the surrounding, and second, the process must be carried out quickly so that there is a sufficient amount of time for heat transfer to take place. So these conditions must be met in order for an adiabatic process to take place. So this is the adiabatic equation. P pressure, V volume is equals to constant. So P is the pressure of the system, V is the volume of the system, and this expression is the adiabatic index and is defined as the ratio of heat capacity at constant pressure, or Cp, to heat capacity at constant volume. So that is adiabatic equation. There are two types of adiabatic processes, reversible and irreversible adiabatic processes. So let us look at first reversible adiabatic process. So reversible is also called an isentropic process, and it is an idealized thermodynamic process. Why? Because the work transfers of the system are frictionless. Okay, take note, frictionless, meaning there is no friction. And there is no transfer of heat or of matter. And the process is reversible. So, it can be turned back such that both the system and the surroundings return to their original states, with no other change anywhere else in the system. So we know in reality no such process as reversible processes can exist. That is why it is called as an idealized thermodynamic process. But of course there are examples. So these are the examples of reversible adiabatic process. So one is extension of springs. Two is slow adiabatic compression or expansion of gases. Electrolysis with no resistance in the electrolyte. The frictionless motion of solids. And slow isothermal compression or expansion of gases. So these are the 5 examples of reversible adiabatic process. Next, we have irreversible adiabatic process. So this is a process in which the system and the surroundings do not return to their original condition once the process is initiated. So this is actually the opposite of reversible adiabatic process. So let's take for example an automobile engine that has traveled a distance with the aid of fuel equal to an amount. So during the process, the fuel burns to provide energy to the engine, converting itself into smoke and heat energy. And we cannot retrieve the energy lost by the fuel and cannot get back the original form. So this is an illustration of what irreversible processes are. There are 3 essential conditions that must be met in order for this irreversible to occur. So the friction that converts the energy of the fuel to heat energy. So there must be friction. The unrestrained expansion of the fluid which prevents from regaining the original form of the fuel heat transfer to a finite temperature, the reverse of which is not possible as the forward process. In this case is spontaneous. Last is mixing of 2 different substances which cannot be separated, as a process of intermixing is again spontaneous in nature, the reverse of which is not feasible. So these are the 3 conditions to be met. So there are 5 also examples of irreversible adiabatic process. First is relative motion with friction. Second, throttling. Third, heat transfer. Fourth, diffusion. And of course, we have electricity flow through a resistance. So that is the 5 examples of irreversible process. And let us sum it up. So there are 4 processes: isothermal, isobaric, isochoric, and adiabatic. In isothermal, temperature is constant, while in isobaric, pressure is constant. In isochoric, volume is constant, and in adiabatic, heat transfer is equals to 0. So isothermal predicts that change in T or temperature is equals to 0. That makes the change in internal energy is equals to 0. Hence, heat transfer is equals to the work of the system. Next, isobaric predicts that heat transfer is equals to the change in internal energy plus work, which is equals to the change in internal energy plus pressure times the change in volume. While isochoric predicts that change in volume is equals to 0, that makes work is equals to 0. So, heat transfer is equals to the change in the internal energy. And lastly, we have adiabatic, which is equals to 0. And this predicts that change in internal energy is equals to negative work. That is all about thermodynamic processes. Thank you very much for the time.